Welcome to Surge. There will be more of you tomorrow, dangerously more of you tomorrow. Last year we had 2 fabulous days of conference, which we intend to have starting tomorrow and the next day. And this year we tried to prefix it with a day of more social event. So we did a hack day, which everyone knows around. They just sit around and talk to each other and don't do anything. That's what a hack day really is. So it's a guise of socialization that geeks aren't afraid of. So we did that today, and we offered 2 really decent training tracks as well that were complimentary of the conference. I don't know, how many people here went to the React training? Awesome. How many people here went to the Chef training? Awesome, too. All right. So I hope you enjoyed that. And tonight, I think that lightning talks are really for entertainment purposes, but apparently there is some sort of knowledge transfer that happens as well. I was actually very afraid that only knowledge transfer would happen and no entertainment would happen. So I asked Jason, who managed the conference last year, to MC and coordinate the lightning talks this year. Actually, I asked someone to ask Jason, because I don't talk to Jason. What I suggested was that I had this crazy experience where someone had to stand up and give a slide stack that they had never seen before that was on the psychological trauma of Facebook addiction, and it was a medical journal slide stack. It was like some PowerPoint awful presentation, and they had to introduce themselves as Dr. So-and-so, and they had never seen the slides before, and it was the funniest thing I probably had seen all day because it was a geek conference and nothing was funny. So I asked Jason to line up all the lightning talks and then finish it off with slideshow karaoke. So I hope that it is as entertaining as it could be. We'll see how that goes. It's always a crapshoot. But you gonna introduce? Yeah. So Jason is coordinating the lightning talks, and right on.
Thank you, sir. Appreciate it. So, again, thanks for coming out, everybody. I'm going to try and make this short and sweet. So this is our first speaker, Rod Cope. He actually was going to speak with us last year, but had to step out at the last moment. So I'm really excited to have him back this year. Rod is actually giving one of the technical talks, so hopefully it's entertaining as well. But everybody, big hand for Rod.
Thanks. All right, thanks. So I got way too much for 10 minutes, so I'm going to start and go fast. Rod Cope, CTO and founder of OpenLogic. I'm writing a book on cloud computing with open source. OpenLogic helps companies with provisioning, support, and governance around open source with a new cloud product. And that's enough intro. All right, everybody in the room probably knows Node.js. It's a very short and sweet description, evented.io for V8 JavaScript. It's pretty much what it does. It gives you asynchronous capability with evented.io. That's great, but it's not the only way to get it. So I want to talk about, especially in Ruby land, which is where I like to live with Rails and Sinatra and all kinds of other good stuff. We like to get some of that benefit too. And there's something called Event Machine, if you're not familiar with it. It's about a decade old, and it gives the same kind of capabilities to Ruby. And just like Node has kind of started this ecosystem that's exploded with a zillion different frameworks and packages and other controls on top, Event Machine has kind of done the same thing. So there's all these very interestingly named projects like Cramp and Celluloid and Coolio on top of it. But there's a relatively new one also. It came out about 6 months ago called Goliath, and that's what I want to focus on. All right, so if we look at Hello World with both Node and Event Machine, this is kind of what it looks like. Probably everybody's seen this. Anybody not seen this? No hands. Okay, you either won't admit it in public or you've really seen this. So pretty straightforward. I spit out a status code, a content type, and hello world. I'm pretty much done. Event Machine is a little uglier, a little nasty. There's more boilerplate stuff going on here. I have this scary thing called a class that I have to write and create this delegated HTTP response thing, something that handles callbacks for me. So ugly, but it does exactly the same thing. You can even see the little 200 text plain hello world stuck in there. So how's it perform? Well, I used trusty Apache benchmark tool and fired 10,000 hits 100 at a time through it. And on, I would say this laptop, this isn't my laptop. I have a MacBook Pro early 2011 model, and got about 6,300 requests per second, which is pretty darn fast. Not too bad for a laptop doing a bunch of other stuff. Event Machine was 9,600. Also pretty darn fast, but it's just static hello world. It's not all that interesting. So let's put at least a very simple framework on top. In Node land, there's something called Express, very popular Sinatra-like kind of framework. Lets you easily write a web app. Looks very similar to what we saw with plain Node, except you don't have to worry about spitting out the 200 in the content type does it for you. In Goliath, this thing built on Event Machine, it's actually a little bit simpler, slightly cleaner with the syntax versus JavaScript, but does the same thing. And because it is a little bit cleaner and JavaScript is a little not so clean, I decided to do is it with CoffeeScript as God intended, so I got rid of all this extra crap with function and brackets and stuff. Now it's about the same. So how do they perform? Well, with our same little Apache benchmark test, and I can run this with Coffee, Hello Coffee, or Node, Hello.js, and you get exactly the same thing because Coffee just translates the CoffeeScript JavaScript first, and it runs it, and they run it the same speed. 4,400 a second with Express, 2,300 for Goliath. That's a pretty big drop. One of the reasons why is Goliath supports this thing called Rack, if you're familiar with that from the Ruby on Rails kind of world. It's middleware that lets you add parameter parsing and format controls and caching and proxying and lots of good stuff. So by bolting that stack kind of capabilities in, it slows you down. But it's not a real app. So let's do something slightly more realistic. Not super realistic, but a little bit. So let's act like we're creating some API. We want to have a count kind of wrapper around it. So when somebody goes to hit our API, we want to look up their IP address in Redis and say, how many times have you called me today? If you're over the limit, I'm just going to ignore your request or return a 403 or something. But if you're not over your limit, I'm going to call a bunch of web APIs to simulate some real work going on, evented IO in parallel, get some results back, and then shoot them down the pipe to you. Okay, so that's what we're going to do. So in either Node or Goliath, there's this setup kind of stuff where I go grab a Redis client and set up some constants like what sites I want to hit and things like that. It's boilerplate, so I'm not going to talk any more about it for the Goliath side. It looks about the same. So Node implementation is all callbacks. Anybody who's done a lot of Node kind of realizes that with all this async programming, everything is a callback. So you're going callback to callback to callback, kind of infinitely nested code. So it looks a little bit like this, where I set up my little app, I grab the caller's IP, I look up in Redis, and that call to the Redis client, when it responds to me eventually, I'll get my callback executed and pass in that current count. So if you're over the limit, you're done. So if that worked, you're not over the limit, then I'm going to make another call to Redis to bump up your count, right, to add one to it associated with your IP, and then wait for that to return. And when that returns, now I'm going to go out and hit those sites. In our case, it's Google and Amazon and Yahoo. I'm going to do that in a for loop, and those will happen in parallel, right? Because Node will take care of doing that in the background and kind of calling me back. So I do that, and so when I get my call back, these can happen in kind of any order. So I need to figure out when I'm done, and one way to figure out if I'm done is to see, have I gotten the same number of responses as I expected to get? So did I hit my total? If I did, then I'm completely done, and I hand the response back to the client. So that's what it looks like. So you can see the little 7 layers of indentation going on. With jQuery deferred, and if anybody hasn't used that, it's a pretty nice way to handle asynchronous stuff going on with jQuery. So you can say, do all these things, and when you're done, do some more stuff, and when that's done and finally finished, kick off this other code. So it's a convenient way to handle some of this async stuff. So with that, and I'm not going to go into gory details here, but you can create something called a promise or a deferred. And so I set that up initially. Then this code looks the same as what we just saw. And now instead of just going straight through Node and hitting those sites and getting responses, I'm going to create an array of promises. And think of a promise as basically, when you call this function, I promise eventually I'll get you an answer. And whenever I do get that answer, I'm going to resolve the promise. So I'm going to call this resolve at the bottom when I have my answer. And that marks the promise as kind of done and ready for it to execute anybody listening on it and say, okay, this thing's done. So I do all that, and then I call this little handy jQuery helper when, and pass in my array of promises and said, when all those things are done, whichever order they come in at, but when they're finished, call this done thing and pass me all the results. And if you're not familiar with CoffeeScript, the ... is like the splat operator in Ruby. It kind of blows out your array into a bunch of arguments. So it's a slightly cleaner, more understandable way to do that. I could do it all with jQuery defer to make a bunch of promises, like a promise to do the get from Redis and another promise that I pipe in using this jQuery pipe thing to say, when that's done, pipe the result of that promise into this next thing, which is a promise, and then pipe that result into the next thing, and then pipe that to the next thing, etc. So it's kind of ugly, messy code. It's not infinitely indented, which is one good thing, but it's still kind of hard to read and understand. So if we do the same thing now in Goliath, here's what it looks like. Give me the IP of the remote caller, look it up in Redis, return a 403 if I'm over the limit, bump it up by 1. Does anything look wrong with this based on what we just saw? Does this look like we'd have a performance issue, a bottleneck issue? Does it look asynchronous? Doesn't look asynchronous. There's no callbacks. That's the magic of Goliath. So with Ruby 192 in fibers and Goliath in this event machine synchrony thing, what looks like synchronous calls are actually asynchronous. So this will perform exactly like Node in that it'll magically behind the scenes go out and do the work, and when it's done, kind of call you back. In this case, the callback is continue executing my code. So it looks simple, straightforward, even though it's asynchronous, which is kind of nice. Now, if you want to realize I am in asynchronous land and don't do all that magic for me, I can expose this thing called a multi, where I say, go do these things in parallel, and then perform them, and when they're all done, kind of wake me up and continue. So it does the same thing as what we just saw, but a lot more straightforward. Performance-wise, it's actually faster when you're using Goliath and you don't have a whole lot of concurrent clients. When you bump it up, they become a little closer in performance, and if you bump it a whole lot more, they're almost identical. So the net result is there's more than one way to do this reactor pattern, even at I/O in the world, especially if you like Ruby or don't like JavaScript or CoffeeScript. You don't have to force it, right? You can get solid performance without the callback hell if you want it. You don't have to use Node. And a nice thing is on JRuby, on OpenJDK, some people have done some early experiments with some flags that will probably cut you to death if you try this leading edge stuff, but they've gotten a 6x performance boost over and above what I already showed you on the event machine side. So something to look forward to. Don't block the event loop. Node makes it very hard to screw up because everything is a callback. In the Ruby and event machine side, you've got to make sure you're using those event machine drivers or you'll block your whole process. And that's it. Thanks. Am I still on? All right. Thanks.
Awesome. Thanks, man. All right. Thank you, Rod. Let's see. Unfortunately, I had to make Rod go first because he's the only one who insisted on sending me PowerPoint slides. Next up, we have John Moore. All right, and so John is chief engineer at Comcast. Wow, you're an evil bastard, aren't you? I'm just kidding. I'm sure you're the one guy that was trying to hold back the monopoly for us, right? No, I'm just kidding. Yeah. Thank you, John. Do you want to use that one?
Yeah, I'm going to use this one.
Oh, one other thing. Okay, so one thing I forgot was Catherine was kind enough to supply me with a pseudo gong. So we are going to start timing, folks. So yeah, keep that in mind. I'll probably give you a 1 minute warning, and then really get noisy.
All right, sounds good. Okay, thanks everyone. So just for clarification, Comcast Interactive Media is the part of Comcast that builds the consumer-facing websites and mobile apps. So we're all web developers, internet developers over there too. So, and yes, that Comcast does have a branch that does that stuff. So anyway, I'm not here to talk about that. I'm here to talk about capacity management and how everything I needed to learn about capacity management I learned at Disneyland. So let's see here. Okay, so how many people are familiar with what this is? This is the Flying Dumbo ride at Disneyland. If you haven't been there, right, this is you've got these Dumbos attached here. You wait for a long time in line. You get on. Elephants go up and down. They go around, and then you get off, right? That's basically it. But for our purposes, this is useful, right? This is something familiar, and this is actually a request processing system. So you may never have looked at this ride this way before, but it's a request processing system. So the way you think about it is that the people who want to ride the ride are your requests. The amount of time they spend waiting and riding, that's the response time for servicing that request. And then you have a certain number of Dumbos on the ride, right? That's your capacity. That's the hardware. And so these are all of the things. These terms are the things you need to understand for capacity management. So we're gonna explain this here. Now, the most useful little bit of thing that we're going to talk about here is something called Little's Law. Ooh, what's going on here? So how many people are familiar with Little's Law? So good. Not everybody. So that means good. Hopefully we'll learn something here. This is one of those knowledge transfer talks. But anyway, this is a bit of queuing theory. But don't be alarmed, because this is all there is to it. It's a very simple equation. But this is one of the most useful equations for understanding the performance and scale of something that you're building. And so what this says is that basically n is the concurrency in the system. So this is the number of people, or the average number of people currently on the ride. X is the traffic, or the rate at which requests are coming in. So this is how many people on average are showing up wanting to get on the ride. And then R is response time, which in our case is how long does a ride around on Dumbo last. And so it's a very simple relationship here. And so effectively what this says is that if we were to actually take a picture of the ride over the course of a day at various points, just like this one, and count how many people were on the ride, and average that out over the course of the day, that average number n would be equal to the average rate at which people are showing up plus, times the response time of the ride. I mean, it seems pretty straightforward, but I can't count how many times that this has actually saved me when I sat down to apply it. So, now that's all well and good for the ride itself, but anyone who's actually shown up and tried to ride on the Flying Dumbo ride realizes that it's very rare to be able to just walk on and just sort of just hop on Dumbo right away. Usually you're faced with one of these things where you have to wait in line. So the question is, well, okay, well, what do I do then? How do I model this? Because it's not enough just to model the ride. I want to model the line too, because that's part of riding on Dumbo is waiting in line, unfortunately. So as it turns out, Little's Law applies not only to entire systems, but actually applies to individual subsystems. And so this is the thing that makes it really powerful. So what that means is, if I look at the number of people in the total system, so that's the people that are either on the ride or in line, right? That's equal to the sum of the people on the ride and the sum of the people in line. But it turns out that people are showing up, right, at a uniform request rate, and there's a relationship between how long you have to wait in line and how long you actually spend on the ride. And this equation holds for the entire system. But it also means that you can look at just the ride, and this holds true, or you can look at just the line, and this holds true. And so what this means is if you have a stack of things here, you can actually use this to analyze various pieces of your stack. Right? So if you look at the incoming request rate to the whole stack just from where it enters your data center, that's the n equals XR on the left. But you can look at the request rates that are coming into each stack and understand the same thing. And so this is really powerful for being able to understand where are your bottlenecks. So now, of course, the next thing about queuing theory is, well, what happens if a whole bunch of people want to ride on Dumbo? And in fact, right, we understand that the Dumbo ride, if let's say the ride lasts for a minute, right, and there are 10 Dumbos, so there's a maximum throughput for the ride, right? I can get at most, I fill up all the 10 Dumbos, run it for a minute, and then that's the maximum throughput. What if more people show up? Or they show up at a greater rate than that? Well, what happens? And so queuing theory actually tells you what happens, which is that a line starts forming. Actually, everybody, this is the funny thing about queuing theory, is that everybody intuitively understands it because you encounter it every day. Every time you have to, if we were British, we would probably understand this better, right? Because we would queue up instead of waiting in line. But But basically, what this is saying is, well, okay, so the line's building up, right, because we're exceeding the max throughput of the ride. And so we know the total people in the system is increasing. Let's assume that this high traffic rate is constant, right? So people are just showing up at greater than the ride can process. So this equation still holds. So if n is increasing and x is constant, then what must be happening to our response time? Right? Our response time must also be increasing. And so this is what leads you to a load test graph like this, right? So if I look at my response time is the y-axis over here, and as I move from left to right across the graph, I'm increasing the load, right? And things look all well and good while I'm under the maximum throughput of the system, but at the point at which I exceed it, guess what? A line starts forming. And in fact, the line, as long as that throughput exceeds the throughput of the system, the line gets longer and longer and longer and longer, and the response time gets longer and longer and longer, and you get this hockey stick. So that's useful for understanding, and it's useful to look at this and to understand where on this hockey stick are you taking a measurement, right? You want to be measuring on the flat part where there isn't queuing delay in the system, because that's actually the performance you're looking for. So we're faced with this problem, right, which is that we have a fixed number of Dumbos, right? So there's 10 Dumbos on the ride. So that's, but we have too much traffic coming in. But we want to put this back into balance so that we don't have this queue growing out of whack. And so we can't affect how many people are coming to the site. And in fact, or to the ride. And in fact, it's popular. We actually want a lot of people to come. So the question is, if X is too high, then the things that are under our control might be capacity and response time. And so those are the things we have to adjust to bring this back into balance. And so there's basically three common strategies for dealing with this when you have too high of a traffic rate. So the first one is, so if the traffic rate's too high, one of the options is to reduce the average response time. And so one option for this is, well, I fail fast. I throw a fail whale up on the site because it's really fast. And I can do that, and so that actually drops the average response time for everything back where things actually fit again, because the errors are fast. So this is why this works. The next option for reducing R is to do performance tuning, right? Well, this takes more time, but in the Dumbo ride, if I ran the ride for only 30 seconds instead of a minute, I could get more people through it, right? So that's always an option. And of course, the last one is you can scale out, right? So the other option, if you can't reduce R, or that's too expensive and you squeezed everything out of it you can always throw more hardware at it. And that may, and there are different time scales for all of these things, right? So you can always add more Dumbos and scale up. So in conclusion, this was a quick run through of Little's Law. It's very useful. It's really a great way with pencil and paper. You can actually use this to find the bottlenecks in your system. So just want to make sure everyone had run across it. Thanks.
I take it that you're next, Mr. Daniel?
I think I am. Let's have a look at the list. We're in such a big hurry here. I don't want to go over my time.
If you want this.
Yeah, I do. Actually, looks familiar.
Okay. There you go. Thank you.
All right, so brief introduction. I'm Daniel Austin. I work for PayPal. Previous to that, I worked for Yahoo. Before that, I was distinguished engineer at Sun. And before that, I was a physicist at a small particle accelerator somewhere in Switzerland that you probably have heard of. I did not work on the LHC. I worked on the SPS, which is the synchrotron proton machine. I don't want to go into the details about that, but it was pre-LHC and basically did the same thing for a lot less money. I want to basically give you 10 minutes worth of quantum computing this morning or this evening. Everybody use Google? Everybody not use Google? Okay, so the Google guys like to talk about how fast everything is, and it really is fast. There's no question that the Google site is really fast, but their search algorithm is not really the fastest one in the universe. We're going to talk about that one tonight. That's where I kind of want to start my talk, if I can get the slides to Progress. Okay, so I'm going to give you the entire talk in one sentence here. The algorithm we want to talk about is Grover's algorithm. It's basically the fastest possible search algorithm in this universe. When somebody gets up and says, oh, it's the fastest possible thing in the universe, the first thing that a bunch of geeks do is say, yeah, prove it. So we'll get to the last slide and we'll talk about how we might prove that. But for the moment, we're going to talk about the fastest possible search algorithm. In the real world, if we want to search things, there's no way we can really make it any faster than going through them one at a time. And that really sucks. So the search is basically, in the order of n. If you have n objects, you got to look at them in order to find the one that you want. Needle in the haystack style. Grover search lets us do this in root n time. Does anybody think that's just amazing? All right, that is amazing. What in the world is quantum computing? Why can we not run Linux and have this happen? Well, we'll get to QLinux. It'll happen, trust me, but it'll be a few years. I can't possibly do quantum computing or any other aspect of physics in 10 minutes. It's just not possible. And I made a promise to myself when I got up here that I would not torture you with any mathematics. So this is a mathematics-free talk. Well, almost. The one thing that I did want to get across to you is some of the qualitative aspects of these things. What is so interesting about quantum computing? Why is it different from what that Linux box under your desk does? What are some of the cool things that we can do? And maybe spark some interest for you guys to go and learn about these things on yourself. There's an endless amount of information about this on the net. You can dig in and get into a lot of depth on this. Really what I want to do is just get you guys to be curious and interested about it. So let's give it a start. How would we go about doing these things? Well, we have ones and zeros in our ordinary computing. Yes, no. In the quantum world, we have yes and no and maybe, which is a new logic state that we've thought up. There's a number of really weird things about quantum computing. One of the most interesting one is that if we run the algorithm, we don't necessarily get the right answer every single time. It's a probabilistic process. If we run the algorithm 50 times, and we might get 95% correctness by averaging across all 50 of those answers. We don't get a deterministic response. We get a probabilistic response. You type flowers into Google, and you might get a flower shop, or you might get a new Star Wars movie. Who knows? Seriously, this sort of thing can happen, and it's that sort of weirdness that makes quantum computing special and really interesting and gets people like you to listen to me get up here and talk about it. A few of the other things that I want to talk about, remember I don't have a lot of time. Teleportation. Yes, we can transfer information from here to there across continents. Nothing passes in between. Literally, nothing passes in between. Super dense coding is a quantum computing technique. You guys will love this one. You actually write down twice the number of operations that you need to do and then only activate half of them. And it works really well. I mean, you only have to do half the algorithm, right? Because in a very RAID, conceptual way like RAID, if you do half the algorithm, you could rebuild the other half of the answer. Sort of, right? Some of the other interesting things that we can do with quantum computing, well, we can run things in different parallel universes at the same time. This will certainly make the AWS guys a little crazy, right? I mean, you thought Hadoop was fast. Wait until we can run your computations in separate threads in separate universes at the same time. You guys are laughing and everybody's going, oh, he's talking science fiction. This is real stuff. We can do multiversal parallelism today. Actually, there's a commercial company, we'll get there, that announced the first pseudo-quantum computing, a quantum computer for commercial purposes, but I'm not going to spoil the rest of the talk. I'll get there. Other strange things that this is interesting for, cryptography. I think everybody has probably heard of this one. We all have an RSA key. They're on our laptop, or maybe it's on our keychain. Well, normally the RSA algorithm is based on the idea that you can't factor some large number into its prime factors. With quantum computing, an algorithm called Shor's algorithm, very different from the Grover algorithm we're going to talk about today, you can factor those very large prime numbers. And in fact, the RSA algorithm was broken via quantum computing simulation in 2008. Sorry, RSA guys, it's all over. I mean, with a number of universes, how can you possibly miss? So what's the current state? I mean, we hear a lot about this, and people are like, oh, is this some paper in Nature? You know, is there anything real out there? Is there some piece of hardware? Is there some piece of software that I can look at? You know, or is this all just, you know, it's Ignite night? Well, there's some real stuff going on there. A qubit, remember, is the analog of a single bit. This is one of those yes, no, maybe guys. We can now do 16 of those. That's 2 words. I think as geeks, we all know that once we get to 2 words, there's some significant computing we can do with 2 words worth of data, right? We're able to actually maintain transient memory for 2 seconds. That's pretty significant as well. If you actually look at the relaxation times for RAM, they can be considerably shorter than that. And there's actually a lot of work that's done to maintain non-volatile RAM for more than 2 seconds in the real world. We can do intercontinental transportation or teleportation. The IBM guys actually demonstrated entanglement in 2006. I'm going to take 13 seconds to talk about entanglement. If I have one system here and one system there, I put them together, I compose a single system, and then I separate them, they're never again 2 separate systems. They're always one system, and they have the properties of a single system. The IBM guys demonstrated this. Some guys at Yale demonstrated the first quantum chip in 2009. They were actually operating on 2 qubits. This is a pretty trivial little device, but they were actually able to use it to turn a light on and off. You can do that with 2 bits, not so hard, right? We can see that, you know, store 2 bits is not such a big deal. Company called D-Wave in Silicon Valley actually announced the first commercially available scare quote quantum computer earlier this year. They threw a huge press event in Silicon Valley. I don't know if anybody saw it. The next day they announced that, God help us, Lockheed bought one. So, no, seriously, they got a contract from Lockheed to buy one of these things. So the real story here is I put a little sign on here, does it really work? The answer is no. This is not a real quantum computer from D-Wave. It's a quantum annealing simulator. It does not do the magic just yet, but it's as close as we've gotten to the magic, and it's still a pretty magical device. Not perfect, but in 2011, we're actually doing pretty good. When I first started giving this talk 5 years ago, I had to get up here and say, we could only do 6 qubits. And so we've made a lot of progress in this time, and this has actually gotten to be a much, much more fun and interesting talk. Let's see how this algorithm called Grover's algorithm works. The first thing we want to know is how do you organize some code? I mean, if it's quantum computing, there's got to be quantum code, there's got to be quantum hackers, there's got to be quantum Twinkies for the quantum hackers to eat while they're writing the quantum code, right? More seriously, what we really got is a set of logic gates. Just like in your digital circuit on your chip, there's a set of gates, very simple. I think everybody probably took this class in school, an engineering class, where you talk about, you know, there's an OR gate and an AND gate and a CNOT gate. All the quantum mechanics model does, or the quantum computing model does, is add some additional gates and modify the existing ones so that they aren't exactly classical any longer. I put a couple examples here for some gates. These are a unitary gate. I promise you no mathematics. This is the part where I break my promise. I just want to give you an example of some of these. You don't really need to know the details other than the fact that these are a little bit of quantum magic that make up part of our quantum program. Now, very easy to see how we can compose this stuff into a real program. Right? So seriously, here's our diagram, and we're just going to go through here. If you look, we're going to repeat this section in the brackets over and over. It's a subroutine, right? And you can see that these are our gates, and we've drawn a little diagram here. That thing on the end, by the way, that looks like a gauge, it's a gauge. This is where we perform the measurement. That's where we get the result of our program out. So this is what the fastest possible search algorithm in the world really looks like. But as geeks, we don't really want to see the UML. We want to see the code. Everybody wants to see code. We're geeks. So if you remember in this picture here, we've got an operation involving H, some stuff in the middle, another operation involving H, and then we go and do this measurement. If you look here at the code, this is our diffusion operator. Here's our Hadamard transform. That's that first operation with H. We just basically call a subroutine. Let's just call it H. Do some inversions, and then we undo that transform. Do this over and over again. This is how we find something in a random database. Now, you look at that and you're going, where's the select statement? I mean, if I'm going to have the fastest database, there's got to be a select statement. What we're really talking about here is, given a very large number of objects, how do we find a needle in that haystack? This is what we mean by a database search when we strip away all the brand names. This is the sort of algorithm that'll do this. Now, I didn't actually write this, I stole this code and then rewrote it with some cheesy comments here. But this is actually written in a language called QCL, Quantum Computing Language, and it basically sets forth all the quantum computing stuff and lets you write these codes. It's actually very interesting and fun to play with. It's a simulator. There are no quantum computers available to us to actually run the code, but to get an idea of what's going to happen, you can go and download the QCL interpreter today and start writing this code and running it and see what actually happens. So, back to how do I possibly prove it? I can't, not in 10 minutes, not on a slide. So I apologize, I cannot prove this. My slides do not contain that much mathematics. I want to give you a sense of how we would go about proving it. I say this is the fastest possible search algorithm. You say, I've got a faster search algorithm. I claim that your algorithm is going to have to run just as many operations of that diffusion operator as mine did. And I can prove that using a fast Fourier transform. Basically, you end up with the same number of terms no matter how you do the search in the fast Fourier transform. I'm not going to trouble you with that kind of math. It'll make you crazy in a 10-minute talk. I just want to give you a flavor of how we would go about proving that. Better people than I proved all this good stuff. It has been proven. Just to finish off, this stuff is real. I did not make it up, although it sounds really cool. It's coming to you. 10 years, we're going to have this stuff. 15 years, you're going to be typing into Q Google. Algorithms are qualitatively different. Remember that business about running in parallel universes and the teleportation. Some quantum algorithms are written in such a way that all you have to do is write the algorithm. You don't have to run it. Once you write the algorithm, there's a 50% chance it'll produce the right answer whether you run it or not. That's actually true. I'm not making it up, right? It's like the quantum world is weird. You don't have to run it. Just write it, 50% chance it'll produce the right answer. We've got the first commercial implementations. We're starting to see in Nature this week, all of these things, cryptography, teleportation, were all big issues in Nature this week. That's about it. The only thing I want to leave you with is just this quote from Feynman, basically. You're all sort of sitting there going, but how can it be like that in this universe? Things don't occupy the same place twice. They don't use parallel universes. Don't kill yourself trying to figure it out. If he couldn't figure it out, we're not going to be able to either. All we can do is learn about it and figure out how to write the code. Thank you.
So if I ever see quantum weirdness as the postmortem for status.amazon.com, I know who to blame. So does everyone here who know who Arthur is? Don't egg him on, please.
Hi. So I was going to put together some slides, and because obviously it's a lightning talk and I'm going to talk about SSDs. But I figured that by now, right, there really isn't any stats that can prove anyone who doesn't believe me. Must be some emotional issues. So I'm going to start off by saying, who here does not have an SSD in their laptop? What on earth are you thinking? Like, someone, please tell me. I need to know. I don't understand this. Laziness, okay. Yeah, okay. Well, that's a really bad excuse. You need a new job. Like, fuck it. Like, you work for a place that don't give you SSDs? What's up with that, man? Yeah, that's unless you bribe someone at Supermicro. That's not true anymore, and especially not in your laptop. That's another good one. So, really, inertia. Who does not have SSDs deployed in their data center? Is that because you're foolish enough to just use EC2? Come on. So, Did I get 5 or 10 minutes? I don't know. Okay. So the slide is up there. Just go buy one. I was actually going to hand out a couple of used X25Ms, but I didn't have the time to wipe them. But one of my employees got a new MacBook Pro, and I gave him 16 gigs of RAM. If you're a developer, you should go out and get your boss to buy one there. It's only $900 per machine. And a 300 gig SSD. And for 2 months, he complained about Vagrant and VirtualBox and VMware Fusion and our install and Chef and everything. And then one day I was like, dude, we need getting your laptop open because he stripped the screws. We went to the hardware store, we replaced it. He went back, he installed this SSD, the RAM, and then he spent roughly the next 2 hours restarting Chrome and starting up 11 VMs and stopping them again and going, oh my God, this is so fast. Oh my God, this is so fast. So basically, the ones of you that don't have SSDs in your laptops, come find me and I'll reboot my machine in front of you, and then you will go and buy an SSD. And I'll even boot up like our entire dev environment. And like, I don't know what more I can do to convince you to go get them. And for the data center, if you don't have them, you can also come up, grab me. I'll log into one of our servers in production and show you what they're doing with these SSDs. And so I was talking to a friend of mine yesterday, on Monday, before I left for here, and he said that his new advice when people come to him and go, what database should I use? Should I use MySQL or Postgres or React, or what should I use? His response is, get a fucking SSD. Right? Like, most of you have data sets that fit on them, so it doesn't really matter what runs on top of them because they're really, really fast. In fact, they're on the order of, fuck, I don't even know. Like, because I'm really tired. And my math skills go away after I see a talk like the one that just happened. But basically, you're going to find that software sucks in ways that you have never imagined before because the drives are suddenly so fast. You're going to find that people do stupid things like putting 10 milliseconds sleep when they don't get mutex because they assume that a read is going to take 8 milliseconds. And you're going to discover that basically every level of the stack sucks because suddenly this assumption that we had this slow piece of shit that's been with us for the last 35 years. Basically, see it as we moved from drum memory to non-drum memory, right? Like, get rid of the raw fucking moving piece of shit in our machines. But you will discover that, like, nearly nothing actually is designed to deal with it. Like, the databases fail, the operating systems fail, the RAID cards fail. Like, they can't keep up. The good thing is that your laptop will keep up. And for some amazing reason, the paging subsystem in OS X at least keeps up. I don't know about Windows. The Intel one, sorry, the Linux one doesn't. The Linux one is just so bad at it, it's sad. So anyway, if you actually want to see how fast they are, just come grab me. I'll show you either on a laptop or on a server what they can actually do. And then if you don't go get one, then I really don't want to talk to you again, ever. Thank you.
I should have given everybody I should have given Archer a PG-13 warning before he went on. But by the way, so I get the title, but who is that in the picture? Oh, okay. So next up, I believe we have Brian Horseman Allen. That's right. Woo! So whatever you do, don't mouse over the bottom because that stupid part will come back on.
All right, thanks. Yeah, so I've used Preview before. All right, as Jason said, I'm Brian, and I'm talking about something that has really annoyed me for about the past 15 years, and the fact that ops people can't really manage themselves. So I'm going to give you a very simple solution to that that's actually helped me for the last 5 or 6 years. Oh, like that. The hell. There we go. So right, the first step of reducing complexity in your systems is just to simplify it, to get rid of it, to reduce it. Unfortunately, this is not often an option. Things are sometimes complex for a good reason. operations is a complex business. And I'm really freaking tired. And most teams are actually really bad at managing that complexity. I'm just going to pick this up because I'm so freaking exhausted. So typically, regardless of how your team works, you can actually get a fair amount of work done. You spend a lot of time spinning around. Hopefully you progress. But it costs far more if you had just started treating it as a project from the beginning as opposed to every day after day of, oh God, why is my face on fire again? So I should probably actually increment slides. So you monitor your systems and services. Apparently I haven't actually used preview before. You monitor your system and services. You monitor services, systems. You grab business metrics, right? Dude. Jason, I'm going to kick your ass for not letting me use Keynote. Right, so you should apply the same methodology and rigor you do to your systems to your own workload. And if you look at manufacturing practices, we're actually nowhere near as rigorous as they are, and we should be. If this is your status quo, you suck, first of all, and secondly, it leads to a fair amount of attrition, a loss of focus, and a loss of productivity in your team and your team members. It's demoralizing, right? If you're just dealing with fires all the time, you feel like you're not actually accomplishing anything on the day-to-day or the week-to-week or the month-to-month. And the thing is, most of us, and perhaps some of us are still, I can't tell who's 20 or who's 30 in this room anymore, we spent the vast majority of our 20s learning this stuff. We sacrificed a large amount of our lives gaining the experience, the skills, and the straight-up muscle memory that we have today. And the fact of the matter is, PG-13 aside, the river of shit has not diminished. In fact, it has increased as we gain more and more responsibilities. And after a certain point, you get to an age where you can't even push buttons anymore. As you get older, you realize you don't have the cycles to deal with this stuff anymore. You have so many other things going on in your life that you can't actually manage the complexity that your job has become. And other things start to seem to matter more. So, and it's entirely possible. There are some guys from OmniTI in here. I'm sure you feel this way about Theo. But either you or your member might actually be a human computer with supreme cognitive powers, but I'm not that. I imagine most of us aren't. I'm just pretty competent most of the time. At the moment, I'm far less so. And I can't actually deal with constant firefighting and interrupts and people casting nonsense on me and actually still expect to get work done and make progress. So I have found minimizing firefighting and keeping track of my work both very helpful and a necessity. No, not you play button. Right? I mean, consider even deep thought needed to create the Earth. Nothing? All right. Geeks that don't love Douglas Adams, there's something wrong in this room. So consider this a metaphor for your life. Your job is to plug in randomly colored wires. And once a month, you get to rewire one of these cables to normalize it. And after 6 months, you rethink your cabling methodology and you start over. And you know, this never gets fixed. So sign up here for your big rock and your hill. This is operations. This is what we do. Like, we plug stuff in, and then people tell us to do it a different way. And on top of this, we're constantly getting interrupts from our bosses, our coworkers, from our systems. Where's my thing? Right? Disks die, your systems explode, your entire cloud dissipates, and the fact of the matter is you have to fix it right now. Whatever you were working on becomes less important than the most recent thing that was pushed onto your stack. So not only is everything on fire, you're constantly being paged about all of this stuff that is on fire, right? So you can't actually fix it because you don't have the mental cycles to do so, to actually think about root causing the issue and actually deploying a fix. Because you're operating on no sleep. You're ineffective. So you just ghetto hack some stuff, you add some duct tape, you add some spackle, and you pray for the best, and the cycle continues. So this is your life, and it is ending 1 minute at a time. So how do we get here? Isn't that pretty? Doesn't that just fill you with a kind of soothing calm? right? Well, the fact of the matter is you need a map for the territory. This is Eisenhower's interstate system, if you don't recognize it, which is pretty ridiculous if you think about when it was built. So we need a map, we need a framework, we need a language. And you, as operations people, need to understand the business, top to bottom. You need to understand your team, your coworkers, and most importantly, you need to understand your customers and their expectations. Yes. And you need a plan. So, ops folks are actually really good at planning for the most part. We're good at strategy and tactics, given a chance. We're good at big and little stuff. We're good at planning out massive amounts of storage and replacing individual disks. We're good at automating 5,000 systems and still tuning a single application. The problem is that ops folks are incredibly efficient magpies. So while we are focused on a single objective, while we're aiming at a single thing to fix, we tend to find a dozen others. Or people just dump them on this, and I make no judgment there. So while you are grinding and reaching for that end game content, you end up with a giant backlog of work, and you can't actually remember a quarter of it, and you don't really know why you wanted those 40 dong bear snouts to start with. Excuse me. And at some point, your infrastructure becomes so complex you can't actually keep it all in your head anymore. And that's fine. That's why you have team members. But in the same vein, you also can't keep the amount of tasks you need to do on that infrastructure in your head either, which is great. I mean, what would happen if your head just exploded? But as bipeds with opposable thumbs, this is actually a very normal situation for you. You've evolved to use tools because you don't have natural offensive and defensive capabilities. But the fact of the matter is you don't have to look like an asshole while you're using them, and you don't have to use crappy ones. And there's a mindset, especially among operations folks, that time tracking and project management tools don't matter. The fact of the matter is all tools matter, and if you have to fight them, if they're not helping you get your work done, you need to find new ones. And bug trackers are not project management tools. You can use them as such, but if you do so, it'll end up driving you nuts. Yeah, 1999 to 2006, this drove me nuts. It was a major, major pain in my day-to-day. And this is subjective, but semantics matter. A bug is not a task. A bug is just some broken shit that you have to fix, whereas a task could be any number of things, including broken shit. But if you're just doing bugs, you're probably just still firefighting, and your life probably still sucks. But there is a very simple solution that's helped me for the past 6 years. And here's a story. So in 2006, I was working at Pobox. And after being there for a while, I decided I had to rebuild the entire infrastructure. How many of us have decided that? Yeah? Yes? Okay. Really? I guess the rest of you are programmers. That's fine. So, I mean, rebuilding an entire infrastructure from scratch is pretty complicated, especially when you're still moving forward. There are many other projects going on in addition to ripping everything down and rebuilding it. So we weren't literally getting a lot done. We weren't getting a lot of traction. In the middle of this, we were switching bug trackers several times, trying to find something that would actually let us manage our work. And finally, Rick Signes, a member of the tech team, realized that we needed an actual project management tool. We didn't just need a bug tracker. And so in addition to this, he also realized that we needed a new methodology. Because we were just working on a stack. Whatever came in got fixed. So you have this huge backlog, and whatever's at the top gets fixed, but the bucket at the bottom never gets emptied. So he found a tool called Liquid Planner. And so the phase shift here is in 2 parts. We generated a new methodology for actually managing our work. And I don't work for Liquid Planner. I just love it. I work for SourceFire. Excuse me. Like many people in this room, I have a cold. Secondly, we integrated the operations and development workflows into a single interface so we could see in one place how we were all doing and how any cross-work requests actually impacted the entire workflow for the deliverable, whatever it happened to be. So this is it. If you're a developer, this is probably really obvious to you. We moved it to iterations, 2-week iterations, in a sprint with a structured workflow. Tasks have a life cycle. At the end of the iteration, we had a meeting to plan the next one. Like, this is all pretty straightforward these days. And it worked. Like, we actually got things done, and I stopped getting paged every 10 hours. It's awesome. And this is it. Like, this is the entire workflow. You have the iteration, which is defined, and you have 3 task lists. Inbox, urgent, and scheduled. Inbox is just for things that come in during the iteration that you then estimate, which is important, and either schedule them for some later iteration, or you just do them there right now if they're quick enough to be done now and not going to impact the rest of your work. Urgent for like the CEO dropping his laptop in a toilet. And then scheduled, which are the things you have promised to get done, your deliverables for that iteration, the things that must get completed. Workflow matters. So if you don't like a complicated view, use a simple one. But the important thing is just to do whatever is at the top of your list. Don't think about it. Don't cherry pick. Just do the thing at the top and do the next thing that comes bubbling up. So it's also important to have feedback while you're doing work so you actually feel like you're making progress. Those blue lines at the end, which unfortunately are kind of cropped off, show me what I'm going to be working on when, which is nice, not just for me, but also for my boss and my team members, so they have some idea when I'm going to get to their stuff. These are all of my iterations since I started working at SourceFire. And if you look at the total done column, you'll notice that I'm not incredibly good at logging my time. So I look like I haven't been doing anything, which makes me look like a jerk. So log your time. Oh, man. We'll just skip over this stuff because it's pretty obvious, except for, oh, crap, my face is on fire. Categorize your tasks so you can find pain points. You can actually determine, excuse me, how much time you're spending on what. And if somebody asks you to do stuff, they have to make you a task for it. They have to respect your time. Because as ops folks, we enable the business. Our job is to make sure that everybody else can do their shit. And if we don't get respect for it, like, what's the point, really? I'm only going to stress that point right there. When you start doing this, don't overschedule yourself. Do 60% or less, because the vast majority of the things you're going to be doing are going to be interrupts for a while. Out of all this stuff, you can look at graphs, you can look at the metrics, you can actually generate stuff like ops folks tends to do. If you find yourself spending 10 hours a week on one thing, that's wrong. You should root cause it and fix it. And at the end of this, you get more sleep, you get to get more work done because it's more efficient, and you get to spend more time on the things that actually matter. So, thank you.